Okay, so today I want to show you how to use this display, which has 25 full color LEDs. And if you've seen my recent videos, you probably already know that I'm testing this display so I can then put it inside the shifter knob. Actually, I already have this shifter knob printed, so I can put this display inside, and this is how it looks like. I believe this is part 4 of this gear indicator inside the shifter knob series. In part 1, I was explaining how to get the current gear by using Hall sensors. Part 2 was about testing this bright LED matrix display. And in part 3, I 3D printed this knob and put this display inside. And so today, in part 4, I will explore this display, which only has 25 LEDs, but they can display full colors, because those are RGB LEDs. But before I do so, let me talk about the sponsor of today's video, which is PCBWay, because sooner or later you might need PCBs or maybe 3D printing or CNC machining, and you can get all those services for a good price on PCBWay. By the way, if you do need PCBs, you can use the link down in the description, and you can get 10 PCBs for free, only paying for shipping. So thank you PCBWay, and let's get back to our project. There are a lot of similarities between this display and the display from my last video. First of all, they are from the same brand, the Pimoroni, and they also use the very same driver chip. On the back of the board you can see this chip, which is the IS31FL3731, and it's driving all those individual LEDs and communicating with Arduino using the I2C connection. There is also one more thing that those displays have in common. Even when this product page says that this display could be used with Arduino, there is no library or sample code. However, I'm hoping to use the very same approach as I was using with the previous display, and that is using the library from Adafruit for this display, which has 9x16 LEDs, and somehow figuring out how those 5x5 RGB LEDs are connected. Actually, let's open the sketch from the last time, which was used to drive this 11x7 LED matrix display, and try to run it with our 5x5 RGB LED matrix display to see what happens. By the way, if you haven't seen my last video, I'm simulating this display using NeoPixels inside this walkthrough simulation. So I'll just copy the code into the clipboard, open the Arduino IDE and paste the code in here. But before I upload it to Arduino, I need to do one small change. While the used chip is the same between those two displays, the default I2C address is not. For the 11x7 matrix, it's 0x75, and for the RGB matrix, it's 0x74. Thankfully, it's listed on the PCB. Which means that inside our sketch, I need to change the address to be 0x74, and then I can upload it to the Arduino UNO. I have the connection prepared from the last time. I'm using this breadboard shield that's snapping onside the Arduino UNO, and then I'm connecting the ground to ground, VCC to 5 volts, and the SDA, serial data to pin A4, and SCL, the serial clock, to pin A5. And as you can see, the display shows some kind of animation. And we are seeing colors because this chip is connected in a way that 3 lines, 3 pins are used for every single RGB LED, whereas previously only 1 pin or 1 line was used for individual LEDs on this 11x7 LED matrix display. By the way, I'm using this 3D printed diffuser. I will show you how to model that and 3D print that later in the video. So we know that the display works, we just need to figure out the mapping between the original Adafruit 16x9 LED matrix display and our 5x5 RGB LED matrix display. And if we do the math, 16x9 is 144, whereas our display, which is 5x5 LEDs times RGB, so times 3, is only 75, which means that not all the pins will be used. I have this sketch from the last time that goes over every single LED of this 16x9 Adafruit matrix display. It first clears the matrix and then sets this single pixel to be lit and prints the X and Y position of this display, which is currently lit to the serial port. And that's exactly the same sketch that I was using to identify individual LEDs on the 11x7 Pimoroni display. Now, before uploading it to the 5x5 RGB LED matrix display, I want to make some changes. First of all, of course, the I2C address is 0x74. I want to set the pixel or the color channel to be as bright as possible, meaning going all the way to 255. And maybe instead of using X and Y positions, let's go with 1D index. So let's imagine I have a display like this, and I will start with 0 and 1 and 2 and so on, going all the way to 15. And then when I jump back to the next line, it will be 16, 17, 18, and so on and so on. So I will add one more entry, and that entry will be named index, and it will be y times 16 plus x. One more thing that I want to do is to have some space around this serial prints, so I'll add a few more serial print line functions, printing just empty lines, just like that, and maybe have a few of those around, so there will be a lot of space around those values, and this way we can identify what is the current X and Y position and the index. And I think that's all I need to do, so I will just upload it to the Arduino. And once the sketch is uploaded, I can open the serial monitor and it should show me the X and Y position and the index value. Now I can look at the display and then quickly look at the PC screen, but what I have done instead was using a webcam, opening the camera application and positioning those two windows in a way that I can see the display as well as the serial output from the Arduino IDE, and then simply recording a screen capture. By the way, I did find out that if you put the camera out of focus a little bit, you can actually see those RGB values a little bit better. So the slightly blurred webcam view is actually intentional. In the end, the screen captured video might look something like this. We have the X and Y position and the calculated index, and we see which LED is currently shining, or which color channel is currently shining. By the way, sometimes you will see multiple LEDs being lit up at the same time. That's fine, that's just an index that we will not use. I will move the video to the side and open Microsoft Excel, and here I want to create a table with our 5x5 LEDs, but for every single LED I need a red, green and blue channel, so R, G and B for the first, second and so on. And let's also color those. And then I can look at the video and see, for example, that this green LED is shining on this position. So this is the position of the LED and it's currently showing the index of being 80. So for the green channel, it will be 80, and continue like this with all the other LEDs. So for example, in here, I will try to find the blue channel for the same LED, which is this one, its index of 96. And finally, the red channel for this LED, it's here, so its index of 112. I will put it inside the table. So for this particular LED, we now have indexes for all the channels, and we only have 24 LEDs to go. It's still quite a tedious task, so I will speed up this section a little bit. That said, recording this as a video did save me a lot of time. Now when we have those indexes, we can find out if they are correct by simply going over every single of them and setting them to maximum value of 255. So back in our Arduino sketch, I will comment out everything inside the main loop, and I will create a new array. Let's call this indexes, and let's actually use byte array because it will not go over 255. And as a content of this array, let's use our table, so copy all those values and paste it in here. And of course we have to Ctrl H to replace tab characters, so tab characters replace with just a comma. And I think that I have to turn on regular expressions for this to work and then replace all. But I still need to add fewer commas to the end of the lines, like so. And then create one more variable of type integer, and let's call this animation and set it to 0. And then inside our main loop, what I will do is I will go over every single of those indexes and light them up using the drawPixel function. So drawPixel function of the X and Y position, but we need to calculate the X and Y position out of those indexes. So I'll just say that this is indexes of the index animation, and to get the X position we will use the modulo function by 16, and then for the Y position we will use something very similar, but instead of modulo function we will divide it by 16. We will wait a little bit, so delay of, for example, 300 milliseconds, and then increase the animation value. So animation ++, and if the animation is bigger than 75, which is the number of indexes, in that case the animation will go back to 0. We will also clear the LED matrix display and wait a little bit, for example 1 second. And I think that we can try to upload it to the Arduino. And once this is running on the real Arduino, we see the red portion of the LED shining, then the red and green, which forms a yellow color, and then red, green and blue, which forms a white color. And since this sequence is displayed for every single LED, we have those indexes right. Which means that we can finally show some custom image or draw something that looks like a custom image. Back inside our Arduino sketch, I will create a new array that will be the canvas for drawing our stuff. So let's call this canvas 5x5 RGB, and let's predefine this with some random pixels. So for example, for the first LED, I want to show the red color, so the red channel will be 255 and green and blue will be 0. The second LED will show the green color, so the red will be 0, green will be 255 and blue will be 0. The next LED will show the blue color, so red, green will be 0 and blue will be 255. Then for example the yellow color is red and green being 255 and blue being 0. And finally the light blue color, the sign will be 0, 255 and 255. I'll just copy this for all the 5 lines. And let's try to display this image or this canvas. So inside the loop, I'll again comment out everything what I have right now and create a new for loop that will go over every single pixel. So pixel going from 0 until I reach the pixel of number 25. I will increase the pixel value. And in here, I want to call the draw pixel function. So just copy the draw pixel function in here. And of course, the value will be based on the canvas 5x5 RGB. But I have 75 values, but only 25 pixels, which means that for every single pixel, I need to set the red, green and the blue channel. So this will be red, green and blue. And I need to set the indexes accordingly. So the index will be pixel times 3. The second will be pixel times 3 plus 1. And the last one will be pixel times 3 plus 2. And of course, I need to use the very same index for also the Y position. So index times 3 plus 1 and index times 3 plus 2. And then for the canvas index, I will use the same thing. So pixel times 3, pixel times 3 plus 1 and pixel times 3 plus 2. And I think that's all I need to do to draw the content of this canvas to our LED pixel matrix. So let's upload this to Arduino. And as expected, we see red, green, blue, yellow and cyan colors for every single line. Now before drawing a custom image, I want to update the walkway simulation from the last project in a way that we can simulate this display, so I don't need to upload it to the real Arduino every time I make change to see the result. This is the sketch from the last time, simulating the 11x7 display using the NeoPixel canvas. The first step is we want to go to the diagram.json file, because now we only have 5x5 matrix display. Then I will delete all those links because I don't need them at this point. And I will change the number of pixels to be only 25. I don't need this canvas and I don't need those images, so I'll delete those as well as the smooth step function and those helper variables. The I2C address is now 0x74, but that doesn't matter for this simulation. And then I will delete this part as well as drawing on the canvas, pretty much most of the stuff except for the NeoPixels. Now from the Arduino sketch, I will copy the indexes as well as the canvas array and just paste it up here. And then we want this part for actually drawing on the LED screen that I will put inside the main loop. And as for updating the NeoPixels, again we only have 25 pixels now. And currently we are getting those values from canvas 7x11, but instead we will use the canvas 5x5 RGB. And we will use this value for the R channel, so red channel. The green channel will be canvas of the index pixel times 3 plus 1. And finally the blue channel will be canvas 5x5 of the index pixel times 3 plus 2. Just like that. And let's restart the simulation to see what happens. And indeed we see the very same thing that we were seeing on the real Arduino, showing the red, green and blue, and then yellow and cyan colors on every single line. So let's finally display some custom image. And let's draw the image first using Photopea, which is a free online graphic editor similar to Photoshop. So in here I will create a new project of only the size 5x5 pixels. Hit the create button and zoom in as much as possible. And let's start with something simple, for example selecting the gradient tool, opening the gradient presets and selecting the rainbow, and then drawing the rainbow, for example like this. And this could be our image. I will save it as a PNG file by going to File, Export as PNG file, give it some proper name and hit the save button. Now to use this image inside our sketch, we need to convert this image into the C-style array. And I have found this online converter which works nicely, so I'll just select the image, make sure to set the color format to RGB 888 and click the convert button. That will create the C file, and there is a lot of things in there, but we really only need the content of this array, so I'll just copy this array and paste it into our sketch. And instead of all those keywords, I will just say it's a byte array, and let's keep the name to be rainbow 5x5 pixels map. Now what I want to do is of course show this rainbow image on our canvas. And it should be hopefully as simple as creating a new loop, going from 0 to 75, or we can say 0 to 25 times 3 for all the 3 channels, and setting the canvas 5x5 RGB value to equal the rainbow 5x5 pixel map, again of the index I. So let's restart the simulation and see what happens. And we see a rainbow, but it looks quite different from our rainbow in Photopea. The first pixel is blue color in walkway, so 0, 0, 255. but it's a red color in photopea, so 255, 0 and 0. And if I select another pixel, for example this yellow one and this blue one, you will see that pretty much the red and blue channels are being swapped, while the green channel stays the same. And because I don't see any easy way how to change this inside the image converter utility, what we can do is simply update the sketch. So the red index will be pixel times 3 plus 2, and the blue index will be pixel times 3 plus 0, so plus nothing. And I will also update it down here, so red is plus 2, blue is plus nothing. And if I restart the simulation now those images should be matching, which seems to be the case. Let's quickly try that on the real Arduino to see if I didn't break anything, so copy and paste this into the Arduino IDE and upload it to the Arduino. And since we see a rainbow that looks like the same as inside the walkway sketch, I think that we are fine. So what's next? Well, let's see if we can animate this rainbow somehow. And to make things simple, let's start with the animated grayscale rainbow. I pretty much want to oscillate between black and white pixels, going over all the grayscale colors. And that oscillation could be easily done using the sine function, which will oscillate like this, going between -1 all the way to +1. But since we need pixels going from 0 to 255, we'll just add 1 and then divide it by 2, and that will go between 0 and 1, and then multiply it by 255. So back inside our sketch, I will comment out this for loop and actually copy it one more time. But this time I will go over every single pixel, so maybe change the index to be pixel, so it's clear what's going on, going from 0 all the way to 25. And let's create a new float variable and call this color grayscale and use the sine function. Now as a sine value, we need some variable that is changing, so create a new variable of type float and call it animation. And set it to 0 for now, and let's actually create one more float variable and call it animation increment and set it to only 0.1. Now inside the loop I will increase of course the animation, saying that the animation equals animation plus animation increment, and then I will use this animation value inside our sine function. Again I need to add 1 and divide it by 2 and also multiply it by 255, just like so. Maybe I can just put those inside brackets as well. And then I want to update the canvas 5x5 RGB value with this new color grayscale value. But this is the float value. I want to convert it to the integer by calling the round function. And our index is now called pixel. And the first index for the red value will be pixel times 3. For the green value it will be +1. And for the blue value it will be +2. So let's restart the simulation. And we see that all the pixels are now oscillating at the same time. To give it some offset for individual LEDs, we need to somehow use this pixel value inside our sine function, so sine of pixel. But if I do it like this, I'm a little bit worried that the pixel going from 0 to 25 is just a very big number, like you can see in here. And inside Desmos, you can see that we are sampling values which are quite far away from each other. So maybe I can divide the pixel by 10 and that should show much smoother animation, although it's still in grayscale. So how do we convert this grayscale animation to the rainbow animation? Well, we are getting the grayscale animation because we are setting all the color channels, the red, green and blue, to the same value. And to get the rainbow effect, we need to offset those values somehow. Let's simulate what's happening in Desmos, so just copy this graph one more time and maybe change it to green color. And we want to offset it, but if I do it like this, it will move it upwards. I need to put the offset inside the sine function, and maybe instead of value, I can put some variable and add the slider, and you can see how I'm moving this function around. But if I want some exact offset, I need to know that the distance between this point and this point equals 2 pi. So let me get rid of this slider, and if I add 2 pi, it will be on the very same position. If I only add 1 pi, it will be right in the middle, but I want to offset 3 channels, which means I'll offset by 2 pi divided by 3, so this will be 1/3. And I will copy everything one more time and add one more graph, and change this color to be blue, so red, green and blue channels, just to visualize those, and the offset will be 2 pi divided by 3 times 2, and now we have all 3 channels nicely offsetted. So if I look into those values, for example in here the color will be red because there is most of the red channel and almost none of the green and blue channels. Here the color will be blue because there is most of the blue channel and almost none of the green and red. And here the color will be green because there is most of the green channel and almost none of the blue and red. And everything in between will be nicely interpolated, creating this rainbow effect. Now we probably don't need to use 2 pi divided by 3 because if I do so 2 times pi divided by 3 is around 2.09. And of course if I multiply it by 2 it's around 4 or 418. So I think that we can also use hard-coded values in our code. So inside the sketch, let's create 3 more float variables being the color red, color green, and color blue, and use the same formula that we were using for calculating the grayscale value for all 3. But let's edit the offset of 2.1 for one channel and edit the offset of 4.2 to the other channel. And then of course when we update the canvas 5x5 RGB array, we use the color red, the color green, and the color blue instead of the color grayscale. So let's restart the simulation, and we should see a nice animated rainbow effect. So let's try that on the real Arduino by copying the code into the clipboard, pasting the code into the Arduino IDE and uploading it to the Arduino UNO. And once it's uploaded, we should see the very same rainbow effect on the real display. And while the animation is running, let's talk about what will be the next steps. Again, I would like to use this display inside the shifter knob to show the current gear, and I think that it will look the best if this number is only in white color, preferably maybe white. However, at the same time, I really like this rainbow color effect, and I feel like that if I only show the digit in white color, in that case I really don't need to use RGB LEDs. So what I have decided to do is to really show the digit in white color only, but during the transition animation I will show some colors. And you've already seen the effect in the beginning of the video. Basically when the number is fading out, it's not fading from white to black color, but instead fading from white to some color, some rainbow color, and then to black color. So there will be this in-between step where you can actually see some colors. So let's do that step by step, and I think that the first step will be drawing this image inside Photopea in white color and displaying it on the display. Drawing the image should be simple. Actually, it's so simple that you can probably type those values inside the code, but I will draw it in Photopea anyway, so create a new layer, then select the pencil tool, make sure the size is set only to 1 pixel, set the foreground color to be white, and start filling those pixels. So maybe something like this could be digit number 3, and then I will go to File, Export as PNG file, rename it to digit 3, and click the Save button. If you want to create and export more digits at the same time, you can create the copy of the background layer, so duplicate this layer and group it together with this 3 layer, and then rename this group to -e-digit 3, and you can continue like this with other digits. So this could be, for example, digit number 2, so this will be digit number 2. I will rename this group to -e-digit 2, then duplicate this group, again delete the content of this layer, and maybe draw a digit number 1. And I know that I'm not going from 1 all the way to the maximum value, but I can continue like this until I have all the digits, and then go to File, Export Layers, make sure that this only export layers with the -e- is checked, and then click the Export Layers button, and that will export a zip file with all those individual images. Then jump to the image converter, and you can select multiple images in here. Make sure that the color format is set to RGB 888 and click the Convert button, and that will create multiple C files. Again, I only needed this array. By the way, if you double click this, it will highlight all the occurrences and you can kind of see the image. So just copy this into our code and paste it up here and rename this to the byte array. I will keep the same name. Currently we are drawing an animated rainbow, and I think I will keep it, but I will create a new loop for every single RGB channel. So just copy this piece around and uncomment it. And for now, try to draw this digit 3 map image. So just copy this image name and set the canvas to be this image of the index I. So if I restart the simulation, I should only see the digit number 3 being in the black and white colors. And now I want to somehow combine the rainbow together with this image. As a first step, I will use this image as a mask for the rainbow. So let's just create a new floating point variable, and let's call this rainbow animated digit, and get the current canvas 5x5 pixel, actually just one channel, but I want to convert this to the float as well, so just cast this to float. So right now we only have rainbow inside, and I want to multiply this with the digit number 3, so where there is a black color, there will be no rainbow, and when there is a white color, there will be a rainbow. So I'll say that the rainbow animated digit equals the rainbow animated digit, which currently has the rainbow, times the digit 3 map. But I want to also convert this to floating point variable, and I only want this to go between 0 and 1, so I'll divide it by 255 and maybe put this inside brackets, and of course set the canvas to be the animated rainbow, and since this is a float, I might round it to integer. So let's restart the simulation, and now the digit number 3 works as a mask for this rainbow effect. I want to create a fading effect of everything, so I'll create one more variable and call this, for example, animation fade. So anim fade, and set it to 0, and of course also the animation fade increment, and set it, for example, to 10. And then inside the loop, I will set the animation fade to be animation fade plus the animation fade increment. And if the animation fade is bigger than 255, and at the same time, if the animation fade increment is bigger than 0, in that case, I will set the animation fade increment to be -10, and maybe also set the animation fade to be 255. And if it's the opposite way, meaning that the animation fade is smaller than 0, and the animation fade increment is smaller than 0 as well, I will set the animation fade to 0 and animation fade increment to +10. So I want to use this animation fade to fade out everything, which means that I need to multiply this rainbow animated digit with our animation fade value. Again, this anim fade goes between 0 and 255, but in order to work for fading, I need to go between 0 and 1, so I will divide it by 255. And now when I restart the simulation, the digit number 3 is also fading in addition to the animated rainbow. But there is still one thing missing. I want this animation to go all the way to the white color. And to do that, I think that I can add this animation fade to the actual rainbow effect. So I will say that the rainbow animated digit equals the rainbow animated digit plus the animation fade. And to see how it looks like, I will comment out the digit number 3 as mask, as well as fading animation, only keeping the rainbow and brightening the rainbow, and see how it looks like. And it looks kind of strange because I think that we are getting over the 255 value, so we should restrict the value to only go between 0 and 255 by saying that the rainbow animated digit equals constraint of the same value going between 0 and 255. And let's restart the simulation one more time. And now it looks much better. So we see the animated rainbow, which is going all the way to the white color. And if I uncomment also the other lines, we see the digit number 3 that is fading in and out, and during the fade animation, we see the rainbow effect. And that's exactly what I wanted to show. Now, if you want to show the digit number 3 in the white color for a longer time, I think that what we can do is we can just increase this number to maybe like 400, and then create a new variable, and let's call this anim fade constraint, and use the same constraint function to constrain the animation fade to only go between 0 and 255, and then use this animation constraint down here, so animation fade constraint as well as in here, and restart it one more time. So now the animation is slightly different, and we see the digit in the white color being displayed for a much longer time. And I quite like the result, so I think that we can run this on the real Arduino. I will copy the code into the clipboard, paste this into the Arduino IDE and upload it to the Arduino UNO. We are only showing the pure white image of the digit, but we still have the hint of the rainbow effect during the transition. So we are not over the top with all those colors, but we are still using the RGB capability of those LEDs. Let me show you one more thing, and that is how to model and 3D print this white diffuser that I was using throughout the video. For 3D printing, I will be using the Bambu Lab A1 mini 3D printer, which despite being the cheapest and smallest 3D printer from Bambu Lab is quite capable. So let's 3D print it, actually let's model it first. And of course the first step as usual is to take calipers and take measurements of all the distances. Once I have all the distances measured, I will jump to Fusion and create a new document, and then create a new sketch on the floor plane. So click the Create Sketch button and click on the floor plane. And I've measured that the size of the one RGB LED together with the white outline, together with the spacing, is around 3.5 millimeters. So I'll create a new rectangle being the center rectangle, and for now I'll just turn this into the construction line because this will be only for helper objects, and draw the rectangle from the center being 3.5 to 3.5 millimeters. And since we have 5 by 5 of those LEDs, I will select everything and then go to create a rectangular pattern and move this arrow up like so. Then change the direction to be symmetric and change the quantity to be 5, and do the same thing for the vertical orientation. So again, change the quantity to be 5 and direction to be symmetric. And now we have the array of 5 by 5 LEDs, so click the OK button. And this is our area where we want to put the holes for those LEDs. Now on my 3D printer, I'm using the default 0.4 nozzle, which means that the line width is 0.4 millimeters. And let's say that I want to put 2 lines between each individual LED, so something like this. Which means that this one will be 0.8 millimeters, so 0.4 times 2, which means that the area in the middle, where the actual hole will be 3.5 minus 0.8. So let's do that. Let's draw a new rectangle, and I will use the same rectangle being the center rectangle, so create a rectangle, center rectangle, but this time I will turn off the construction line and draw from the center, again being 3.5 minus 0.8 for both sides, so 3.5 minus 0.8. Then I will again duplicate this rectangle into the array by going to create a rectangular pattern, move it to the top side and to the right side, change the quantity to 5 for both vertical and horizontal orientation, and set the direction to symmetric for both, like so, and click the OK button. So we have all the holes and we have all the outlines for those LEDs, but we need the outline for the actual board. And I measured the outline of the board to be around 19 millimeters, but let's do some math to calculate the right value. And what I mean by right value, obviously, is I want to use this 0.4 nozzle, so I want to either use 2, 3 or maybe 4 of those lines around. If I measure the current size from this line to that line, that's 17.5 millimeters. And I want to add wall lines until I will get closer to those 19 millimeters, so 17 times 5 plus, and again I'm using 0.4 nozzle, but since I'm doing walls on both sides it will be plus 0.8, so times 2, that's 18 times 3, and if I do it again, that's 19 times 1, and I think that this is the value that I will use. So I'll draw one more center rectangle, create a new center rectangle from the center, and set the size to be 19.1 for both width and height. On the bottom of the board there are 2 holes for screws, but what I'm thinking is using our diffuser in a way that I will extrude some geometry to snap inside those holes. Which means that I need to make this slightly bigger to include this area, and I've measured this size of the board to be 23 millimeters tall, so I'll create a new rectangle, start from here and then go over this point and set the height to be 23 millimeters. Yeah, I have a lot of measurements, let's just move those around a little bit, like so. And then inside this area I want to have 2 circles. I will click the circle tool and I've measured the radius to be 2.4 millimeters for both, so one circle and the other circle also 2.4 millimeters. I want those to have the same vertical position, so I'll create a new line and turn this into the construction line and draw it from this center to that center. Then click this OK button because I only need one line, and click the horizontal vertical constraint and click this line. So now they are aligned nicely, and it looks like that those circles are also aligned with those LEDs. So I'll use the same trick by drawing a new construction line from this center to that center, and then from this one to that one. And click the same horizontal/vertical constraint and click this line as well as this line. Since I can move those circles around, it means that we are still missing one distance, and I've measured the distance between one of those edge LEDs and the center of the circle to be 3 millimeters. So I'll select the Sketch Dimensions tool and draw the dimensions from the edge of this LED to the center of the circle and set it to be 3 millimeters. And I think that's all that we need for our sketch for our board outline. So click the Finish Sketch button. Then maybe rotate the 3D view a little bit so I can see it from the side, and we can start extruding individual areas. First of all, I will extrude everything, and I did some testing and I found out that 2 layers of white PLA is translucent enough, and since I'm using the layer height of 0.2 millimeters, I need to extrude it by 0.4 millimeters. So select everything and click the extrude button and actually extrude it downwards by minus 0.4 millimeters. That will be the front diffuser. Then open the sketch and maybe I will rename it as well. Make sure it's visible and select again the extrude tool and then click this outline and this outline. And we will start extruding it for those LEDs, and around 3 millimeters works just fine. I will just quickly change the material so it's a little bit lighter, so set the appearance and maybe use this aluminum setting for this body. And then I want to extrude those 2 circles so they are snapping into the PCB. I will quickly hide the body, select the extrude tool and click this circle and this circle, then show the body again. And in the extrude dialog, I will change the extent type to be to object and click this top face, but I want this to be offset a little bit more, so I'll set the offset to be 1.5 millimeters, which is the thickness of the PCB. So click the OK button, hide the sketch, and this is our white diffuser. Then I need to right click the body and select Save as Mesh, select the 3MF format and click the OK button. Now I wasn't really sure what should be the distance between the diffuser and the LEDs, meaning how much this should be extruded, so I've created a few more different versions. So I've selected this extrusion step, right click and select Edit Feature and create few different variations going from 2 all the way to 5 millimeters. Have a proper names, so 5 millimeters right now, and again Save as Mesh, and I've exported 4 different meshes. Then I started the Bamboo Studio and imported those files by going to File, Import 3MF Files, and used the Arrange All Objects function to arrange those on the plate. I'm using the default 0.4mm nozzle with the white PLA, using the 0.2 layer height, and pretty much all the settings are left to default. So the only thing left to do is to click the slice plate, which looks like this, see if there are any problems, which doesn't seem to be the case, and then click the Print Plate button. And after clicking the Send button, the file will be sent to the 3D printer, and it will jump to the Device tab where we will see the live stream of the webcam. Since I have the AMS unit, the automatic material selection unit, the printer will change the filament by itself, then it will do the autobed leveling, and then it will start printing. As you can see on the bottom of the screen, all those 4 pieces take about 22 minutes to print, but the calibration in the beginning takes about 5 minutes, which means that we need about 5 minutes per piece. And so once everything is 3D printed, it looks something like this. The good news is that those diffusers snaps onto the display quite nicely. We just need to select which one will be the best. The taller is the diffuser, the more evenly is the light spread, but of course with a higher diffuser we lose some brightness. In the end, I think that the 3mm version looks the best. And again, this is how it looks like when the display is placed inside the shifter knob, which is of course also 3D printed. But I will talk about it more in the next video, of course if there is enough interest. And that's pretty much it for today. If you have any comments or questions, please put those down in the comment section. All the source files are on GitHub, the link is in the description. Thank you very much for watching and I hope to see you soon. Thanks and bye.